You know, if you were to ask me, hey Leo, how do you know when you have mastered a topic or mastered a certain subject? I would say it's when you can approach a problem from different perspectives and still reach the same conclusion. When you can do that, you know you have arrived and you know you understand what's going on. So in today's video, that's what we're going to do. We're going to solve one beginning physics problem, and we're going to solve it from 4 different perspectives, and we're going to see if we're going to be able to reach the same conclusion. And if we can, then we know that we have mastered our beginning physics course. All right, so let's dive into it. Okay, so before we get to the problem, let's talk about the different perspective that we're going to be talking about today. So let's start with perspective number 1, which is forces. Newton's second law, which is F equals ma. Force causes a mass to accelerate, F equals ma. If we want to know how any object is going to accelerate, all we need to do is sum up the total forces acting on that object, because the total forces acting on that object is what is going to cause that object to accelerate. So that will be perspective number 1. Now let's go to perspective number 2. Perspective number 2 has to do with a physical term called mechanical energy. Mechanical energy is defined as the total kinetic energy plus potential energy of a system. Kinetic energy has to do with energy of motion, and potential energy has to do with energy that is stored within a certain force field, such as gravitational force field. Now the question is, what will cause the mechanical energy of a system to change? And the answer to that is non-conservative forces. A non-conservative force is any force for which you don't know the potential energy, which means that it does not have a constant force field. So basically, you know a force is conservative if you can write down the potential energy for that force. If you can't write down the potential energy for that force, then that force is a non-conservative force. If there are non-conservative forces acting on your system, your mechanical energy is going to change. And the extent to which it changes is going to be equal to the amount of work done on the system by the non-conservative forces. And another way that mechanical energy can change is if there are inelastic collisions occurring within the system, because when the blocks crash into each other, they're going to deform, they're going to stick together, and all of that is going to require energy. And in such a situation, the extent to which the mechanical energy changes is going to be equal to the work done by those internal forces that deform the objects. Now, perspective number 3, you've learned about linear momentum. So that's momentum along a straight line. The momentum of an object is the mass times the velocity of the object. And momentum, just like mechanical energy, it has a very good conservation law. Momentum is going to be conserved as long as there are no external forces acting on your system. And the extent to which the momentum is going to change is going to be equal to the impulse given to the system by the external forces. Impulse is the force times the time. How long did that force act on our system? Now we move on to the 4th perspective, and that has to do with angular momentum. Now, angular momentum, just like linear momentum, is going to be another conserved quantity, except that angular momentum has to do with circular motion. Angular momentum is objects moving along circles or curved paths. Angular momentum will also be conserved unless there are external torques acting on the system. Torque is force times radius. It's the radius relative to some pivot point, relative to the fixed point of rotation. And angular momentum is going to be equal to the mass of the object times the velocity times the radius. And the extent to which torque will change the angular momentum of your system will be equal to the torque times the duration of time. These 4 principles are coherent and consistent with each other, and we need to be able to see that. So let's go ahead and answer one question 4 different times to make sure that we can apply these 4 different concepts for a single problem. All right, so let's get to the question. Okay, so the question says a 3 blocks massless pulley system is shown in figure 1 when m equals 3 kg. What is the acceleration of the blocks when they are released from rest if the kinetic coefficient of friction for the table is mu sub k equals 0.15? With a system like this, a major assumption is that the rope does not stretch. The length of the rope is constant, and therefore if the rope moves, the entire system moves, because all 3 blocks are connected to the rope. The block on the far left, which has a mass of m, is hanging on the left side, and therefore the force on that block will cause the entire system to slide down on the left side. But on the other hand, we have another hanging block on the far right side, which has a mass of 5m. And that block is hanging on the right side, and gravity is pushing down on that block. And if that block falls down to the right, all the blocks are going to shift to the right. And of course, we can't forget the frictional force acting on the table, which is going to slow down the rate at which we fall. You have a light block of mass m on the left side, and you have a heavy block of mass 5m on the right side. So which one is going to win? clearly the heavy block, the 5M block. So this system is going to slide down to the right side, and it's going to be slowed down by the frictional force acting on the block on the table. And what we're trying to figure out is, what is the acceleration with which this system is going to be shifted to the right side? So let's use F equals ma to figure that out. Now, we just said that the driving force for the motion of this block is going to come from the heavy mass hanging on the right side. It's the extent to which gravity pushes down on that block. So the force that the heavy block exerts in the system is going to be 5 mg. But then on the other side, we have the lighter block on the left-hand side that's going to oppose that force. So we're going to have to subtract the extent to which that block pulls to the left, and that block is going to pull to the left with a force of mg, because that's the force of gravity acting on that block. And then we can't forget to add in the force of friction. Friction is going to act in the same direction as the light block, which is going to slow down our motion. And force of friction is equal to mu times n, right? Where n is the normal force. Normal force acting on that block on the table is equal to its weight, because the block is laying flat on the table, right? And therefore the force of friction is going to be equal to negative 0.15, which is the coefficient of friction, times 2 mg, because the block has a mass of 2m. So we have the total forces acting on our system, and the net force is going to be equal to ma, right? And ma is the mass of our system times the acceleration of our system. So the sum of these forces will be equal to 8 ma, which is the total mass times acceleration of the system. And now all we have to do is solve for a. We get 3.7 g equals 8a. The acceleration is going to be equal to 3.7 times g, which is 9.8, divided by 8, and that is going to give us a total of 4.5 meters per second squared. And that is going to be the acceleration of the system. So we already know the answer is going to be answer choice D, but we're not just looking for answers, right? We're looking for understanding. So let's move on to method 2. For method 2, we're going to analyze the mechanical energy of the system. Mechanical energy will only change if there are non-conservative forces acting on the system. We already saw that the two main forces acting on our system were the force of gravity acting on the heavy block and the light block, and the frictional force acting on the block on the table. So we have gravitational force and we have frictional force. Gravity is a conservative force. We know the potential energy for gravity. Frictional force is a non-conservative force. Frictional force depends on your direction of motion. Gravity always does the same thing. It brings you down. It never changes direction. So gravity is conservative, friction is not. So the extent to which our mechanical energy is going to change is going to be equal to the work done by friction. Friction sucks the energy out of a system. So our mechanical energy for this system is going to decrease by the amount of work done by friction. And the work done by friction is going to be equal to the force of friction times the distance through which the force acts. Remember, work is equal to force times distance. And from the first method, we saw that the force of friction is mu n, and the distance through which that force is going to act is going to be some distance we'll call h. And when we simplify this, it equals negative 0.3 mgh. So now let's go ahead and analyze our mechanical energy directly. Initially, these three blocks were at rest, which means that none of these blocks were moving, which means that the initial kinetic energy was equal to 0. Now, what was the initial potential energy? The thing about potential energy is that what matters is the difference in potential energy more so than the absolute value of the potential energy. So we are given the freedom to set our zero potential energy at any point. So I'm going to set the initial potential energy of the system equal to 0. So the initial height of the system is going to be equal to 0. Therefore, my initial mechanical energy is going to be equal to 0. Now, what is our final mechanical energy? After we release the blocks from rest, the system is going to shift to the right. The block on the far left is going to rise, the block on the table is going to slide to the right, and the block on the far right is going to slide down. Which means that after we release the blocks from rest, they're going to start moving. All three blocks are going to move at the same speed. Therefore, the total kinetic energy for our system is going to be equal to 1/2 8mv squared. Because remember, kinetic energy is 1/2 mv squared. The total m is going to be 8m, and they're all going to be moving at some final speed called vf. So that's going to be the final kinetic energy of our system, and the potential energy of our system is going to change. We started off at initial height 0, but then the block on the far left is going to be shifted up, and it's going to be shifted up by the same distance h that the second block was shifted to the right. So the potential energy for the block on the far left is going to go up to mgh, which is the potential energy for gravity. And also, the potential energy for the block on the far right is going to decrease. is going to decrease because the height is going to decrease. Therefore, it's going to lose potential energy, and its potential energy is going to go down to negative 5 mgh. So this is going to be our final mechanical energy for the system. Our mechanical energy final minus our mechanical energy initial is going to be equal to 1/2 8mv squared plus mgh minus 5 mgh. And this difference is going to be equal to negative 0.3 mgh, which we already calculated initially. And when we simplify this equation, we get 4v final squared equals 3.7 gh. You should know from your kinematics equation that if you have a system under constant acceleration, the square of the final speed minus the square of the initial speed is going to be equal to 2 times the acceleration times the distance the system moved. And we were already told that our initial speed was 0 because our system was released from rest, which means that our final v squared is going to be equal to 2ah. We get 8ah equals 3.7 gh. And now all we have to do is cancel out the h from both sides and solve for a. And when we do that, we get a equals 3.7 times g, which is 9.8, divided by 8. And once again, we get 4.5 meters per second squared. So we got the same answer by approaching this problem from a mechanical energy perspective. All right, so far so good. Y'all keeping up? Let me know if you have any questions. Now we're going to solve this problem by analyzing momentum. The momentum of a system is going to change if there are external forces acting on the system. The external forces acting on our system are the forces of gravity and the force of friction. Therefore, the change in momentum for our system is going to be equal to the gravitational impulse, which is going to be the force of gravity times the amount of time that gravity acts on our system, plus the frictional force times the amount of time that the frictional force acts in our system. Force of gravity hanging on the block on the left is going to be equal to mg, and that force is going to try to cause our system to shift to the left. So that's going to be equal to negative mg delta t. And the other area where gravity is acting on our system is on the heavy block on the right, and the gravity acting on that block is going to cause the system to shift to the right. The impulse generated by that force of gravity on that block is going to be equal to 5 mg times delta t. Of course, we already said that our system is going to shift to the right, so friction is going to act to the left. So the impulse generated by friction is going to be equal to negative 0.3 mg times delta t. And when we add all these terms up and simplify them, we get delta p is equal to 3.7 mg delta t. So now let's go ahead and analyze the momentum of our system directly. So our initial momentum is going to be equal to 0 because initially nothing was moving. Remember, momentum is mass times velocity, but we had no velocity to begin with because our system was at rest to begin with. So P initial equals 0, easy. But then once we release the system from rest, the system is going to start to shift to the right due to the heavy block. So they're all going to have the same speed, and therefore the final momentum of our system is going to be equal to the total mass, which is 8m, times the speed vf. All three masses are going to move together in one direction. So our momentum final minus our momentum initial is going to be equal to 8mv, which is equal to 3.7 mg delta t. We get 8v equals 3.7 g delta t. So now once again we kind of run into the issue of not knowing what our final speed is, but we know what the relationship between our speed and acceleration is. For constant acceleration, final speed is going to be equal to the initial speed plus the acceleration times delta t. V initial was equal to 0, and therefore V final is equal to A delta t. And this gives us 8A delta t equals 3.7 G delta t. And we can cancel out the delta t's from both sides and solve for A. And once again, we get 3.7 times 9.8 divided by 8, which equals 4.5 meters per second squared. All right, so now that's three methods and we got the same answer. So it looks like we understand what we're doing. But let's go on to the fourth method to make sure that we really understand all the different concepts of beginning physics. So the fourth and final method would be the method of angular momentum. Angular momentum is similar to linear momentum, except that angular momentum deals with rotation. In order for our system to translate and move, it has to slide across the pulleys. As the ropes slide down on the pulley rotates to let the rope down so that the system can move. So the rope generates rotational motion at the pulley. And remember, the entire system is connected to the rope because all three of the blocks are tied together by the rope. So to analyze the system, all we have to do is look at the change in the angular momentum occurring at the pulley. And remember, angular momentum is only going to be changed by external torques. and the extent to which the angular momentum is going to change is going to be equal to the angular impulse that these torques are going to generate. Once again, the two forces that are going to pull on the rope are going to be the force of gravity and the frictional force. So the change in angular momentum of the system is going to be equal to the gravitational torque times the change in time plus the frictional torque times the amount of time that friction acts on the system. Torque is the radius times the force, and the radius is going to be the radius of the pulley. So let's start with the gravitational force acting on the heavy block on the right side. It's going to cause the pulley to rotate clockwise. So that torque is going to be a positive torque. Therefore, the angular impulse for that force is going to be equal to 5 mg times the radius of the pulley times delta t, which is the amount of time that torque acts on our system. And on the other hand, the block on the left side is going to pull the rope to the left. And if you pull the rope to the left, it will cause the pulley to rotate in a counterclockwise direction. So that's going to be a negative torque. So that torque is going to be equal to negative mg times the radius of the pulley, r, times delta t. And then we also have friction, which is going to translate to pulling the rope to the left side. So the torque generated by friction is going to be equal to negative 0.3 mgr times delta t. And when you add all these up, you get 3.7 mgr delta t. So this is going to be equal to the change in the angular momentum of our system centered at the pulley. Now remember, angular momentum is mvr. Initially, there was no speed. V was equal to 0. Therefore, the initial angular momentum was equal to 0 because there was no motion initially. So there was no angular momentum. But then once we let the system go from rest, then the rope begins to slide down. So we generate angular momentum at the pulley when we let the system go. And what is the angular momentum that we generate at the pulley? Well, angular momentum is equal to mvr, right? And we know the r is the radius of the pulley. V is the speed with which the system moves. So it moves with some final speed v. And the mass is going to be the mass of the system. Because remember, as the rope slides down on the pulley, the entire system moves with the rope. So the amount of mass that the rope carries is equal to the entire mass of the system, which is 8m. The rope slides down on the pulley with a speed vf at a radius r, and it carries a mass of 8m. So the final angular momentum of the system is going to be equal to 8mvr. So the change in our angular momentum is going to be equal to 8mvr minus 0, which is just 8mvr, and that's going to be equal to 3.7 mgr delta t. And we can go ahead and cancel out the m's and the r from both sides, and we get 8v equals 3.7 g delta t. And once again, the final speed is going to be equal to the acceleration times delta t. So we can plug in a delta t for vf, and we get 8a delta t equals 3.7 g delta t. Cancel out the delta t's from both sides and solve for a, and we get a equals 3.7 g divided by 8. And once again, we get 4.5 meters per second squared. Whew! All right, so there you have it. We solved one problem 4 different ways, and I guarantee you, if you were able to solve this problem in those 4 different ways and actually understood the concepts, you have basically mastered your beginning physics course, and congratulations on that. All right, so let me know if this video was helpful. Let me know if you have any questions about it. Go ahead and leave them in the comment section below. And if you appreciate the content that we generate on this channel, go ahead and give the video a like. Go ahead and subscribe if you're new to the channel. We're happy to have you on Intuition. And as always, I'll see you guys in the next one. All right, bye-bye.